Check it out now, y'all.
nanoHUB-U, online instruction.
Hi again. We're back to start week 2 of the course Fundamentals of Atomic Force Microscopy. And in week 2, what we intend to do is we intend to take the discussion that we had in week 1. We're going to take the fundamental result, which is the 1 over z to the 6th dependence of interaction potential energy between two molecules. We're now going to incorporate that and try to understand what the implications of that are for a tip interacting with a flat substrate. So we're moving more away from the physics and we're getting more into the fundamentals of atomic force now. So the basic problem, of course, is that we've spent a fair amount of time talking about how two atoms or molecules separated by a distance z interact one with respect to another. What we'd like to do is we'd like to integrate that interaction potential energy over all the atoms in the tip and over all the atoms in the substrate to get the net resultant interaction between the tip and the substrate. So that's the plan for this particular lecture. By way of summary, this is a slide from the previous lecture. The net result is that the interaction potential energy depends on a constant c, van der Waals. It's proportional to 1 over the 6th power of the separation between the atoms and the molecules. There's a minus sign that indicates that the interaction potential energy is negative. That indicates an attractive interaction between atoms or molecules that undergo these van der Waals forces. To start with, we'd like to think about the simplest case you can imagine, and that's one atom or one molecule interacting with a flat plane. And what we're going to do now is we're going to start to transition to a set of coordinates or a set of variables that will make sense specifically for atomic force microscopy. And so in particular, we're going to say that the atom or molecule is located at a distance d above a flat plane that has infinite extent to it. We're going to assume that the interaction potential between the atom outside the plane and any particular atom inside the plane is governed by this 1 over z to the 6th van der Waals interaction potential energy that we've already discussed. We're also going to assume that the interaction potential energy is the sum of only pairwise molecular interactions. So that means that 3, 4, 5 n-body interactions are not included. And what that basically means is that if molecule outside the substrate, in principle, it could interact with the molecule inside the substrate. It could polarize that molecule, and then that particular molecule could polarize, let's say, a third molecule in the substrate, and the polarized third molecule could then interact with the first molecule to form a 3-body interaction, let's say. That's completely neglected in this discussion. All we're worried about is the interaction of this molecule with each individual molecule in the substrate. No intermediate interactions are considered. And lastly, it's worth pointing out that this whole discussion neglects important details. And one important detail could be, for instance, the fact that the atoms on the surface of the plane are completely different. They could be oxide atoms compared to, let's say, atoms inside the bulk. So those subtle effects are neglected in this discussion. Everything's assumed to be, all the atoms, all the molecules in the substrate are assumed to be the same. To sort out this problem, the math is given here, and there's a simple geometric diagram that helps you sort out the arithmetic. Basically, we're going to consider the interaction of an atom outside the substrate with a ring of molecules indicated by this these little red symbols. These little red symbols are intended to indicate a ring that's actually symmetric about the zeta axis. The interaction is going to depend on the number of atoms in that ring, and the number of atoms in that ring is going to depend on the number density of atoms or molecules in the substrate. So this number density is not the mass density, it's how many atoms per cubic meter there are in the flat slab that we're being considered. So the calculus to sort this out is indicated on the slide, and what's interesting, I suppose, is the last equation, which says that when you integrate this van der Waals interaction potential over all the atoms, molecules in the substrate, you'll end up with an expression for the interaction potential energy that varies as 1 over the distance cubed that the atom or molecule is positioned above the substrate. So the 1 over z to the 6th potential, 1 over the z to the 6th variation of the interaction potential between individual molecules gets integrated down by the algebra to a 1 over d cubed answer. The number density of elements, just to give you an idea of what the quantity rho 1 is in this particular calculation, I just provide a quick table that indicates the number density for the elements in the periodic table. Typically, the number density is on the order of 10 to the 28th per cubic meter. The exact number depends on how the atoms arrange themselves, and you can get numbers straight away from this table. So that's like the first step that in the process of understanding how a tip interacts with a substrate. The next step in this process is to take that result and now integrate it over a sphere which has a radius r tip. And we're going to then form the net interaction between a sphere and a substrate, and we're going to use the sphere to approximate the tip. So to do that, we take the result that we just obtained, a 1 over d cubed dependence, now becomes a d plus zeta cubed, because zeta is going to tell where the particular atom or molecule is located in the tip with respect to the substrate. And we have to integrate the position of that atom or molecule over the geometry defined by the tip. And that's the arithmetic behind that is sketched out in this slide, which basically takes the spherical tip, splits it into small slabs of infinitesimal thickness d zeta. We integrate the interaction potential energy of all the atoms and molecules in that slab with the substrate. Again, the arithmetic is worked out for you if you're interested in those details. The interesting result at the end of the day is shown by the yellow box at the last equation. And the yellow box says that the interaction potential energy between a sphere and a substrate, if the sphere is located a distance d, if the apex of the sphere is located a distance d above the substrate, right, the interaction potential energy varies as a constant h, which depends on the number density of the atoms or molecules in the tip and in the substrate. It depends on this van der Waals coefficient C that we discussed in week 1 of the class. Depends on the radius of the tip, and it's now inversely proportional to the separation d between the tip and the substrate. So the d to the 6th, the z to the 6th dependence in the van der Waals interaction potential, after you integrate it out through the various steps that we've indicated here, that ends up as a 1 over d separate variation of tip substrate interaction, as we indicate here. So this quantity pi squared rho 1 rho 2 times the van der Waals constant c, that's often referred to as the Hamaker constant. And there are various symbols used for the Hamaker constant that you'll find in the literature. Some people just represent it as capital H. You'll also find articles where it's represented by capital A or capital A sub H. They all tend to refer to the same quantity. So it's the product of the number densities times the van der Waals constant that describes how the two atoms or molecules interact one with respect to another. So this is a fundamental result that shows up time and again in discussions of atomic force microscopy. And it's based on the model that the tip can be approximated as a sphere, a smooth sphere, and that sphere is the apex of that sphere is positioned a distance d above an infinitely flat substrate. I mentioned in the last lecture of week 1 that these pairwise interactions between individual molecules, they tend to emphasize molecular parameters, and it's a fair question whether you can do that calculation using a model that emphasizes the bulk properties of a solid. And that is done in a theory that's been developed by Lifshitz and his co-workers. That theory was developed in the early 1960s, and it replaces the parameters polarizability and ionization potential. It replaces those by static dielectric constants and frequency-dependent dielectric constants. And the details of that calculation aren't terribly important for us within the context of this course. I write down the final answer for the Lifshitz expression for the Hamaker constant, right? And now you can see that all the parameters involved in this expression relate to the bulk properties of the solids involved. So the notation is intended to represent a solid 1 interacting with a solid 2, and the intervening material between solid 1 and solid 2 is referred to as material 3. And to evaluate these integrals, you need a model for the dielectric constants, especially the frequency-dependent dielectric constant of typical materials that you deal with. And that model is well developed in the textbooks. The frequency dependence of that model in particular is interesting, and what I try to do in this slide is remind you what the dielectric constant, the frequency dependent dielectric constant of a material is trying to represent. And it basically is trying to show you how a solid responds to an electric field that's incident on it at some frequency f, right? There are different regimes of interaction. At very low frequencies, the electrons in the solid become polarized. This is the standard discussion of a dielectric inside of a capacitor plate, where the charge is separate, physically separated one from another. And that model applies very well for low frequency electric fields. But as the electric field increases, as you start to get into the microwave region of the electromagnetic spectrum, then the interaction between the electric field and the solid focuses more on dipole-dipole interactions. As you go higher in frequency into the infrared, you start to get interaction between the electric field and the atomic polarization of the atoms or molecules that comprise the substrate. And then lastly, in the visible region of the electromagnetic spectrum, the interaction is actually a polarization of the electronic charge cloud. And the point to take away from this slide is that every time you go through one of these characteristic regimes, right, the imaginary part of the dielectric constant is going to have a local peak associated with it, and that indicates that there's an energy loss mechanism that's turning on in a particular frequency range. And likewise, the real part of the dielectric constant has this characteristic signature where it goes through a sort of a bipolar shape response that's related to each resonance. So what you can show is that if you model the frequency dependence of these dielectric constants with, for instance, a real simple model that applies for most solids above the visible range of frequencies, then the expression that Lifshitz derived can be rewritten in terms of the static dielectric constants epsilon and the index of refraction of the materials that are involved. So this is really a nice result because the static dielectric constants are something that you can look up. The index of refractions N are also quantities that you can look up. And so that if you're trying to understand how, let's say, a tip of material 1 interacts with a flat substrate of material 2, and if the intervening material is referred to as material 3, you just need to know the relevant dielectric constants and indices of refractions in order to estimate H, the Hamaker constant in the Lifshitz approximation. And once you know that constant H, you can then estimate what the strength of interaction between the tip and the substrate might be. So I just worked through a typical example. I go through the effort of putting in numbers. This is the case where a tip made out of silicon dioxide interacts with a flat silicon wafer, which also, for all intents and purposes, has a thick oxide layer on it. And let's pretend that the intervening material, in this case, the intervening medium is water. I just list the relevant parameters and I work through the calculation here so you can see how you can start to estimate the Hamaker constant from known optical properties of the solids. Typical values for Hamaker constants, you can find them scattered in the literature. I've not been able to find a really systematic source of Hamaker constants for a wide variety of solids. What I do here is I've copied some results from various literature papers that I've read for materials that are kind of interesting for atomic force microscopy. All right, so now we're no longer interested so much in the molecules or the atoms, but we're starting to focus more on the solid materials that tend to make up tips and substrates that we use. And you can see that depending on whether there's a air medium between the tip and the substrate, or in the case of when you submerge the tip and the substrate underwater, right, you can start to see how the Hamaker constants vary one from another. So in summary, okay, it's probably useful to step back and try to summarize what we've achieved up till now. We went through a rather lengthy discussion of how two molecules interact, and we tried to understand what the interaction potential energy between these two molecules might be. That's given by the first cartoon on this particular view graph. This is the 1 over z to the 6th potential, 1 over the z to the 6th variation in potential energy. If the molecule interacts with a flat slab, then we showed that the interaction potential energy varies as 1 over d cubed, where d is now the distance between the molecule and the flat slab. We then integrated the molecule over a sphere, radius r sub tip. When you integrate that molecule over the radius of a sphere, you end up with this very famous expression that says the interaction potential energy is the Hamaker constant h times the radius of the tip divided by 6 times the separation distance between the apex of the sphere and the flat plate. And in the next lecture, or in lectures later this week, we'll also consider the situation of two flat planes interacting with one another. And I just write down the answer for that here, so we have a slide that's reasonably complete summarizing the important results. I'll also mention that the answers you get for how the interaction between two solids, how that varies with separation between the two solids, it clearly depends on the geometry of the two solids. Machiavelli's very nice book gives a discussion of these different geometries, and I just take a slide from his book and incorporate it here just to remind you that the answer is going to depend on what the two objects look like. So just a few comments, right, to remind you that this is a model, and how well that model applies to a real physical situation depends on how well the assumptions of the model matches the physical situation. So one of the big assumptions, of course, is that we're assuming that the surface and the tip is perfectly smooth. It's really hard to achieve that experimentally, but clearly if you want to do these integrals, that's one assumption that you have to put in. And it's possibly one of the shortcomings of these models is that you never have a tip that's atomically flat. You'll never have a substrate that's atomically flat. So if you see deviations of experimental results with this theory, possibly that's one of the points that you have to worry about. So I think that summarizes discussion of Hamaker constants. And if you come back for the next lecture, we'll continue this discussion and use it to launch into a discussion of surface energies between different solids. So we'll see you for that lecture.